In this lecture, we're going to talk about limitations that you might experience when conducting investigations or measuring or reporting data. And since one of the big goals of science is to report the data that we find, it's really important that we report that data in as appropriate a manner as possible. We have to first remember what measurements tell us. Measurements are used by scientists and a variety of other people to describe substances, conditions, or phenomena, or even processes or things that we observe. So in doing those reportings, I guess, we use a large variety of devices, and those devices have a huge range of precision. Just think of a beaker, for instance. We have beakers in the lab that measure anywhere from 25 milliliters all the way up to 1,000 milliliters. So you can take measurements, say, of 25 milliliters using this huge 1,000 milliliter beaker, but it's going to be really hard to be very precise. It will be hard to tell exactly where 25 milliliters is on a device that's designed to accommodate 1,000 milliliters. If we use a tiny beaker, right, there will be more gradations between 0 and 25, and it will make it easier for us to be a little bit more precise. That leads us to our first definition. Precision is a term that in science is defined as the degree to which a certain measurement can be reproduced, or how easily can someone else take a measurement and get the same data that you have gotten. It's very heavily dependent upon the measuring device that's being used, and different measuring devices lead us to a variety of levels of uncertainty. So uncertainty just simply describes the fact that we are limited by the device that we're using. If we have this 1,000 milliliter beaker, for instance, the gradations here are probably going to be 100, 200, 300, 400, 500, if we're lucky. More likely, this beaker might only have 250 milliliters, 500 milliliters, 750 milliliters, and then 1,000. In that case, there's a whole bunch of uncertainty between, say, 0 and 250 milliliters. We would be doing a lot of guessing, which means there would be a high degree of uncertainty. It's also possible, particularly in the high school lab, that the skill and the attention of the person doing the measurement could lead to a level of uncertainty as well. That's not to say that you are not trying to be as precise as possible, but sometimes we aren't always the very most detail-oriented as possible when we're in the lab. Some other limitations that we have in forming measurements is that we can do our very best to be as precise as possible and to pour very slowly, say, into our beaker, and to use a little dropper to add drop by drop of water. But sometimes, despite our very best efforts, we end up with measurements that are nowhere near the actual measurement of that object in real life. This term accuracy helps to describe that discrepancy. So the accuracy of a measurement describes how close our measurement or our reported data is to the true value for an object. A lot of times the true value will be something that I know or your text gives you, and then you'll compare your data to the true value data. So in reporting data, it's really very, very critical that we make sure the data we report communicates to the reader or whomever happens to be looking at our data. We have to be sure that we communicate the work that we've done without over-representing ourselves as being better than we are, or having measurements better than we are, or having measured something that we didn't actually measure. And so that leads us to a term that we're going to be using all year, and that is significant figures. Significant represents just the numbers within a measurement that we actually physically saw on the device we were using, plus one number that was estimated. So take a look down here at this example. Let's say we were given the task of measuring how tall everyone in the class is using meter sticks. So we take student X, maybe, and student X is 164 centimeters tall on the meter stick. We can see that the top of his head comes to 164 centimeters. But maybe the top of his head doesn't hit exactly at the 4. Instead of the top of his head being exactly at the little hash line for the 4th centimeter, 164 centimeters, let's say maybe his head is just slightly above 164 centimeters. Most people would represent that as 164.2 centimeters or 164.5 centimeters or some other estimation that represents something between 0 and 9 and is some fraction of a full centimeter. This first number that is estimated, because this number doesn't show up on the meter stick, but we have a pretty rough idea of what it would be based on the hash marks on the meter stick, that's called the estimated number, and it is significant because you can visually estimate it. So that leads this measurement of 164.2 centimeters to have 4 significant figures. That tells us as the reader that there are 1, 2, 3 numbers that are known to be true. They were seen on a device, and a 4th number that was estimated to as close as possible. Some other examples of how we might use this. Here's a little graduated cylinder down at the bottom of the page. And this graduated cylinder has gradations that measure from 0 to 100 milliliters. You can see the 0 here is represented just by this flat line. There isn't an actual 0 written. And then you can see 10, 20, 30, blah, 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 blah. So if we pour water in, say up to this level maybe, we can estimate, well actually we can tell how much water is in there at first by just observing how full we made it. I'm just going to erase the top so we can see. So let's say we were all the way up to this line here. Sorry, it's a little hard to reproduce that line there. There we go. And we were all the way up to that line there, which on this device is going to be 55 milliliters. I can see the 50, I can see 5 hash marks, and then we're up to 55 milliliters. We can also assume one more place just based, looks like my N got cut off here, sorry, I'm doing 2 things at once now. We can also assume part of a milliliter, and in this case, I think my little fake line is pretty close to being right on that 5 hash mark. So we're going to say that our estimated number is 0. There are no additional milliliters, which takes us from our 2 known measurements, 55, which we can see on the device, plus our 1 estimated. So that's a 3 significant figure measurement. 1, 2, 3. If we were to fill this graduated cylinder all the way to this top line, all the way to 100, or maybe even slightly above, that would lead us to a 4 significant figure measurement because we would have 1, 2, 3, 4, depending on how slightly above 100 we poured. So you can see that different devices have varying levels of significant figures and varying levels of uncertainty. There are some rules for figuring out how to tell what reported data is significant. So when you are reporting data, obviously you report every number you can see plus the first one that you can estimate. But a lot of times you'll be given data to evaluate, and it's important that you recognize which numbers within that data are significant. So the first rule is every non-zero digit, so every digit from 1 to 9, is significant when reported in data. So here we have 4536. We'll pretend that that's grams. It's going to be something pretty heavy. But 4536 grams has 4 significant figures because every single one of those digits is a non-zero. We will quite often use zeros, and we will quite often be reporting data that is less than 1. That's a small, small number. Zeros to the left of a non-zero digit, they're called leading zeros. Leading zeros are not significant. They are simply placeholders to show us what fraction of 1 is being represented by this data. So over here, if you look, we have 0.00033, and maybe this is in, oh goodness, I don't know. We'll stick with grams. So 0.0033 grams again. All of these zeros are insignificant. They are not measured. They're simply reporting that this measurement of 33 tens, hundreds, thousands, 10,000ths of a gram is a very, very small number. So in this instance, there are only 2 significant figures in this data. The zeros following a non-zero digit are called trailing zeros. So when we have all of these non-zero digits, 1 through 9, and then we have trailing zeros, the zeros are only significant if they are actually measured numbers or estimated numbers. So in this case, we have 563.0. Because the decimal is reported and then there's a 0 following it, this represents that this number was measured, 563 point, was actually viewed on a measurement device, and the 0 was the estimated number. That's what the decimal tells us, that the 563 decimal was a measured number. However, when we see 563 and with a 0 following it and no decimal, that 0 becomes insignificant because, again, it's also just a placeholder. It's sort of like the same as the rule above. It's just telling us that we are 10 times larger than these numbers that have been specifically measured. So there are only 3 significant figures in this case. The only time zeros on the right are significant is if they both follow another digit and they follow a decimal point. And we'll do lots of practicing with this. The last rule that involves measurements is exact numbers. There are lots and lots of instances where we use numbers that are precise. They've been counted, for instance. We count the kids in our classroom. There's no uncertainty there. It's not possible that I missed a whole kid in the room, or that there's a leg but not a body that goes with it and I didn't represent that data. Right? That's an exact figure. And so exact numbers have exactly certain, there is no uncertainty in their significant figures. So we consider them to be infinitely significant. Every single digit is significant, and we will never be limited by that data. You'll see what I mean by limited in just a second. Some examples of exact numbers are things like conversion factors that we use that are precise, 5,280 feet in a mile, 24 donuts in a bag, etc. Finally, we will do lots of calculations, tons and tons of calculations that involve significant figures, both in data that you have collected and data that you have been analyzing. So some of the calculations that you are likely to do, the first one involves addition and subtraction of significant figures, and these go together because they're just opposites of one another, which you already know. So whenever any data is added or subtracted, we use the least number of decimal places to limit the significant figures in the sum. So for instance, let's say we have this first number, 35,466.01 plus 12.334. The first number, while it has more digits overall, has the least number of decimal places. So we're going to be limited in our final report to no more than 2 decimal places. So when we add these up, we get 35,478.344, and we have to limit that number down to just 2 decimal places, so we chop off that final 4, and we are left with 0.34 as our reported number. When numbers are multiplied and divided, again, opposites of one another, we use the least number of total significant digits in our initial data. So again, I use just the same numbers here, but in this case, 12.334 only has 5 significant figures. So we are limited in our final answer to just 5 significant figures. So when we multiply these together, we get 437,437.7673. We have to cut that number down to just 5 significant figures, which means we are going to lose all of these digits. And that leaves us with 437,430. And actually, I rounded that improperly. What a knucklehead. So what would happen here is we're getting rid of this 7 because it is not a significant figure as limited by our calculation. And so the 7 has to become a 0, which is just a placeholder, which means we round up the 3 to a 4. So I misreported this data to you. And that would make our final number 437,440, because the 0 at the end, a trailing 0, is not significant. We only would have 1, 2, 3, 4, 5 significant figures. It's important when doing calculations that you always do the full calculation. Don't limit yourself at all till you get to the very, very end. And again, this last rule, which I just mentioned at the last slide, is that exact numbers do not limit the number of significant figures. So let's say we were multiplying this number by 12 months in a year for whatever reason, then we would be limited not by the 12, but by the 1, 2, 3, 4, 5, 6, 7 significant digits in that first number, because this is a measured number. So it has limitations, right? We're limited by the device being used. This would be an exact number because it was counted. So the smaller number of limited digits determines how many digits we have in our final product. So what I would like you to do, as always, is bring some discussion questions to class. I cannot imagine you don't have some questions because this is a whole bunch of new information. So bring at least 3 discussion questions written in your notes and then write a brief summary and we will talk. Thanks very much.